All right, so another thing that's going to get used with our vectors is we're going to talk about something called the dot product. Um, what the dot product is going to end up doing here is it's going to help us determine if two vectors are parallel or if they're perpendicular to each other. So we're going to be looking at that. We're also going to be trying to find the angle between two vectors. And the dot product is something that gets used later on. Once you get into, if you end up taking calculus, you use it there as well. So just kind of to show you the operation of a dot product. So dot product here, what it is it looks like you are doing multiplication, but you're not. You're taking vector u and you're taking the dot product between vector u and vector v. So you'll see that I have u dot v. What I'm going to be doing here is I'm going to be taking the first components of both of the vectors. I'm going to be multiplying them together, and then I'm going to be adding that to the product of the second components by multiplying those together. Properties of the dot product that we can be used, if u dot v is the same thing as v dot u, so it's very similar to 2 times 3 is the same thing as 3 times 2. Something new for us that we'll be looking at is when you take the dot product of u dot u. So if you take a vector like that, usually that would be squaring it. Here it's going to be looking at actually taking the magnitude and squaring it. 0 times dot product, or 0 dot any vector is always going to be 0. And then if you could kind of use your distributive property as well. So u dot the sum of vector v and w, you could take u dot v plus u dot w. And then your scalar multiples here too, ku dot v, well, we could rewrite that as u dot kv, or you could do u dot v times k. So just some different properties that are being used. So here is an example of using the dot products. Like I said, what we're going to do is we're going to take the first components, we're going to multiply those together. So I'm going to take 3 times 5, and then I'm just going to add it to the second components being added together. So then we'll add it to 4 times 2. So 3 times 5, so that's going to give us 15, and then we're going to add on 8 to it. And so our dot product here is 23. Even if you have vectors that have negatives, we can do the same thing. So take the first components, multiply those together. So 2 times 3. And then we're going to add on the product of the second components being multiplied together. So -1 times -5. 2 times 3 is 6. -1 times -5 is a +5, so we're going to add those together, and we end up with a +11. Now, when you are finding the dot product, what it is really it is another way to find the magnitude, or what we've been talking about is the length of a vector. When you are taking and trying to find the when you're trying to find the magnitude of a vector, so 4 comma -3 here, we would do our a squared plus b squared equals c squared. You're using your Pythagorean theorem. Well, if you take the square root of the dot product, you will get the same thing, because if you take your dot product, you're multiplying the first components together. So 4 times 4, that's giving us our 4 squared. -3 times -3, that's our -3 squared. So the dot product in just a single vector is another way that you can find the magnitude. Just kind of one way that you might see sometimes vectors being written out is sometimes you see them as linear combinations. It's just kind of a fancy way of rewriting these vectors. They just use variables instead of the actual little brackets that are being used. So the vector of AB can also be associated with AI plus BJ. 3, 4, 3i plus 4j, 2, -1, 2i, -2j. Well, when you're working out with this vector, you're going to treat it just like you would any other vector. So 3i plus 2j, we're not going to multiply I times I and get I squared or anything here. We're just going to be thinking of this as vector of 3, 2 dot vector negative 2, 5. And so we're going to go ahead and do our dot product. So I would take 3 times the negative 2, and then I would add it to 2 times 5. So a negative 6 plus 10 ends up giving us a positive 4. And so here we would end up with 4 for the dot product of the two. Sometimes you see it written out this way I think I've seen it more so kind of in the engineering aspect of things, more so with your electrical engineering and problems based off of that. All right, so hopefully that has enough examples for you to just identify what the actual dot product is itself. Now what I want to do is talk about some different ways that we can apply our dot product to some different things, and that's going to lead us to trying to find the angle between two vectors. So if we were to look at these two vectors that are created here, vector v and vector u, and they're both going in opposite directions. If we're trying to find the angle that's between them, what we could do, setting this up here, is if we knew vector w, then we could use our law of cosines in order to do so. And what this next formula that I'm going to give you, it comes from the law of cosines. Now, if you're interested in the proof and how this is derived from there, you can go ahead and find some extra reading on page 468 in your book, but I'm going to save the 20 minutes, and I'm just going to go ahead and give you the formula that's being used. So to find the angle between two vectors, what we can do is set it up as the cosine of theta, so the cosine of the angle between your two vectors is equal to the dot, so u dot v, all over the magnitude of u times the magnitude of v. And as we know, if we're going to try and solve for an angle, that's where our inverse cosine comes in. So by taking the inverse cosine of that quotient right there of your dot product and then multiplying out your two magnitudes, you will end up with your angle between two vectors. So let's go ahead and look at an example. So we're going to try and find the angle between vector u and vector v. So looking at our two vectors here, what I'm going to start out by doing is I'm just going to break this down so you can see it. I'm going to take u dot v, so we're going to take 2 times the negative 2, add it to 3 times 5, so negative 4 plus 15 is going to give us 11. So our u dot v is 11. Trying to find the magnitude of vector u. That's what we've been doing these past couple days, and that's really your Pythagorean theorem. So the square root of 2 squared plus 3 squared. 2 squared is 4, 3 squared is 9. So we've got 4 plus 9, and that's going to give me the square root of 13. Magnitude of vector v. We're going to take the square root of negative 2 squared plus 5 squared. Negative 2 squared, well, that's going to give us 4, and 5 squared is 25, and so now I get the square root of 29. So now what we're going to do is we're going to take these three parts. We're going to take the dot product of vector u and vector v, and we're going to divide that then by your magnitudes of vector u and vector v. So we have the cosine of theta is equal to 11 divided by the square root of 13 times the square root of 29. I can go ahead then and find our angle by taking the inverse cosine of all of this, 11 over the square root of 13 times the square root of 29. And I probably should have had my calculator up and warming up here, but I'll do it off to the side here. You're going to want to make sure that you are in degree mode, since you're trying to look for a degree here. So let me just change over my calculator, get in degree mode. And I'm going to take the inverse cosine. And I'm going to take 11. And then be careful, some of you might want to simplify this down first. But we're going to take 11 divided by, and make sure that you're taking the product of, so I'm going to put an extra parenthesis in there, the square root of 13 times the square root of 29. And then I'll close both of those parentheses up. So we want to make sure that we're putting our, that square root of 13 times the square root of 29, make sure that that's staying in your denominator there. And so then we end up with 55.49 degrees. For some of you, you might want to just multiply this out first, and so you might just want to take 11 divided by the square root of 377. So square root of 13 times the square root of 29, just take 13 times 29, and then you could do the inverse cosine that way, just so that you're not worried about trying to put on all the parentheses that you possibly need. All right, so that's how you find the angle between two vectors. Now let's talk about orthogonal vectors. So orthogonal is a new word for us, and what that just means is it means that two vectors are perpendicular to each other, which means you've got an angle of 90 degrees that's between them. So if that is the case, then that means that the cosine of 90 degrees of vector u dot vector v over the magnitude here, we could just end up working that out. Well, cosine of 90 degrees, if we think about where 90 degrees is in the cosine of that value, that is 0. And so if you're trying to think about what's going to happen in order for this formula to be 0, the only way that can happen is if your numerator equals 0. Your denominator cannot equal 0. Now, you can't have a magnitude of vectors u or v be 0, because then we would have a problem. You'd be working with just a single point. You wouldn't be actually working with a going in any direction or any distance. And so you would have no angle that's created right there with just a point. With vector u and vector v, they need to be some sort of length here to be able to talk about that magnitude. And if we want the cosine to be 90 degrees or the angle to be 90 degrees between these two vectors, we need it to then be cosine of 90 degrees, which is 0. So what this just means is that when you take the dot product of two vectors, if it equals 0, then right away, right then and there, you know that between those two vectors, it has to be perpendicular to each other. Now, you can definitely go through all the motions that we just did on this last example to find the angle between them being 90 degrees. Or if you go ahead and you find your dot product, so if I do u dot v, and I take 2 times 4, and I add 4 times a negative 2, we're going to get 8 plus a negative 8, which gives us 0. So that means that vector u and vector v right here are orthogonal vectors, meaning that they are going to have to be, that they're going to have to create a 90-degree angle. So then there you go. Now, what about when we talk about vectors being perpendicular, we also want to talk about, well, what if vectors are going to be parallel to each other? If vectors are going to be parallel to each other, then that means they need to be going in the same direction. Now, they might have different lengths to them, which is okay. So they might have different magnitudes. But what we have to look at here is that the direction is going to be the same. Well, if vectors u and v are parallel to each other, then what happens is one vector becomes a scalar multiple of the other one. So vector u equals some multiple of vector v. So for example, I have u, vector u is negative 10, 6, and vector v is 5, negative 3. So if I set this up and I look at, okay, I've got vector u, which is 10, 6, and I'm looking at, well, is there a scalar multiple that I can be looking at so that this ends up working out? We talked about scalar multiples back when we were dealing with operations, where really this is just saying that k times 5 would have to equal negative 10, and k times negative 3 would have to equal positive 6. So now if I go ahead and I set this up, I divide by 5, k here would have to equal negative 2, and I get here that k also has to equal negative 2. The fact that I could now take and put a positive 2 in for k, that tells me that these two vectors would be parallel to each other. They're going to be running in the same direction. Really what you're looking for is you're looking for the slope between these two vectors, because we know that two vectors, if they have the same slope, then they are parallel to each other. Well, here, if I look at them, if I go, this is going to be my run and my rise, so over 10 and up 6 is the same thing as going over 5 and down 3. We're going in the same direction. Our rise over our run is going to be the same because that's what parallel lines are. So if you have a scalar multiple, then you know that they would have to be parallel to each other. All right, so 16 minutes, not so bad, or 17 minutes. So please use the rest of the time now to work on the assignment in the book. You can grab the books off the bulk shelf and then make sure that your ACT is all set to go for tomorrow as well. So I'll see you guys tomorrow.